All right, hey everybody. Well, this might be your first experience with the flipped classroom, as I called it. I'm doing this today just so that we can get through some basic chemistry, stuff that I think is review for some of you, but for some of you, you may need to go through this, so I wanted to go through it quickly. You feel free at any point to pause it, go backwards. That's the beauty of this. If you're absent, you obviously get to still experience this without having it in class. We'll do some practice to make sure that you are up to speed after I finish all this. But I definitely want to go through, it's important stuff to understanding the next chapter. We're kind of now getting into chemistry, and I know that this is a biology course, but in order to understand biology, you have to understand basic chemistry, terminology, and basic chemistry information. So these are the notes that you have in your possession. You may not be able to see too much detail as I can see it, but you have it in front of you, so it's probably, you can assume where I'm writing these things. So a lot is vocabulary based. The first word we see on here is inorganic chemistry. Inorganic, and the next chapter is organic, and some people will get that confused based, they use the word organic, they throw it around a lot nowadays. And organic is going to be a carbon-based chemistry. Inorganic is kind of a lot more, it's not the focus carbon. It's included, we can talk about it, but it's not the basis for this, this chapter. It's really a broad spectrum chemistry. Atoms. You've used them probably before, and what we have here, the atom, let me make sure I'm not on the right. Okay. So atoms, we will define it as the smallest unit of a chemical element. So you've heard of many elements out there, such as gold, iron, aluminum. The smallest element of the smallest atom of that element is an atom. So it's composed, you can't break that up. If you broke that atom up, it would no longer be that element. It's the smallest component of it. There are subatomic, if you look at the prefix sub, it means below. There are things that are smaller than atoms, which you're familiar with. The first one being a proton. And a proton, some information you want to write down is its location. It is located in the nucleus of the atom, which is more towards the center. It has a mass, I'm not going to write nucleus, you can write that, but it has a mass of 1 AMU. AMU stands for atomic mass unit. It's kind of a made-up term. It's just a really small unit, so they kind of made that up. There is an equation out there, I think, that says how much an AMU stands for. Not really important for our course. But it has a mass of 1 general AMU. The next one, information about protons, is it has a positive charge. And that will be important to understanding some other stuff. The next one, a neutron. A neutron is also found in the nucleus. If you do not know that, you need to write it down. It has the same mass as a proton. It's classified as a 1 AMU subatomic particle. Many people will try and do like the P is positive, so they might get confused with N is negative. That is not the case. It is neutral. Did I spell that right? No. All right, EU. It is neutral, so it doesn't add to the charge of the actual atom. And the last subatomic particle is electron. The electron has been located, there's different terms for it. They might say it's in an orbital. They're trying to get away from that now. In the future, as you progress through school, you're going to find that they call them energy levels, because energy is often associated with electron, so they really hit that hard in the beginning to make sure that you realize energy and electron. So these are somewhat, you can't draw energy levels, so they still draw them as orbitals, and sometimes just for simplistic sake, we are going to use that term orbital just because it's a little easier to comprehend. Electrons do not have any mass. They're so insignificant that they actually say it's a 0 AMU. Obviously, it is matter, so therefore there is going to be a mass, but it has no real effect on the overall mass, so it's generally a 0. This one has the negative charge. So those are some things that you need to know. An element, I'll have you write this down to speed up time, is a pure chemical substance consisting of only one type of atom. So if I have an element, and you can see over here to the right, there's a picture. This is an element, this is mercury, and for many of your parents and things like that, this would be something that they would actually use in school. We've gotten rid of it because of its toxicity and what they have said potentially can happen. Our thermometers used to be filled with it, now it's filled with an alcohol that has the same component. So then, the next thing, here we have the, here we have a square, which would be found on the periodic table. And so if you have a periodic table, you can look at this. Here's an example. Some stuff that you get from a periodic table. What we have here is a number. If you find Hg is the chemical symbol for mercury, and there are tons of them out there. You can look at this periodic table and see all of them. You don't have to memorize them for my class. It's not a necessary thing. So Hg is mercury. There are two numbers. There is a smaller number that is a whole number. On this one, it's 80, and it would be found in numeric order on the periodic table all the way up there. So you find 80 on your periodic table. Below, you have a number 200.59. From periodic table to periodic table, it may vary slightly. There's no universal number. But we're going to talk about what these two represent. The 80, or the whole number on any one of these squares, is going to represent the atomic number, which is right here. So you can fill in what the atomic number does. This is the total number of protons found in one nucleus of the atom. So you can write that, the total number of protons. Because every atom is electrically stable and or neutral, you've got to have a balance of negative charges to equal out all the positive. So if this technically tells you how many protons there are, it indirectly is also going to tell you how many electrons in one atom. We will find that that number will change slightly when it starts to bond, but for what you need to know right now, the atomic number does say the number of protons. If you change that number, you change the protons, and therefore you change the element. Changing the number of electrons does not automatically tell you you have to change the chemical that you're working with. The atomic mass is the other number. This is the larger number. It sometimes is a decimal place. You'll learn in chemistry as to why that is a decimal place. Not really important for the biology aspect. But what this tells you is anything that has a mass in this atom is going to contribute to this number. So therefore, the two things that have a mass are the proton and neutron. With that, the 200 tells you protons and neutrons, when added up together, their mass is 200. Since everything is 1 AMU, I can use my process of deductive reasoning to tell you that since 80 must be protons, that must be 80 of the 200 represent the protons and the mass. So that means that there must be 120 neutrons to compensate for the rest of the mass that has to get up to 200. You can round it if you want to round it to 201 and say that there's 121 neutrons. I'm not going to be that specific because these numbers do fluctuate. So for this instance, if you do round it to 0.59, you can round it up to 201, and it'd be 121 neutrons, 80 protons. 80 electrons because it does equal the same number of protons. So you can do that. You can write those numbers down here. Proton 80, electron 80, and then technically 121 if you round. All right? So there's some basic information. The next page. Isotopes. Isotopes are going to be defined as two elements, or atoms of the same element. Atoms of the same element with varying masses. So the same element tells you that it has to be the same number of protons. So the only thing that can vary and adjust the mass would then be the neutrons. Common isotopes involve the atom of carbon. So if we look over here, we see three variations. In this term, they still have the two numbers, but they've rounded both of them, a 12 and a 6. Because the higher number has to be the combination of protons and neutrons, the higher number is the mass, the lower number in this case is going to be the atomic number. It is the same in all three variations. The thing that is going to vary is going to be the mass, 12, 13, and 14. To simply determine how many neutrons you have, you're going to subtract, again, 12 minus 6. So therefore, according to the periodic table, this is the one that's on there, the 12 and the 6. So you're going to have 6 protons, 6 neutrons, and 6 electrons. Because 12 minus 6 is 6, that tells you neutrons, and because the number is 6 there, the atomic number, both protons and electrons have to be. The carbon is written as C12. The 12 in this form will represent the atomic mass. So you'll see other elements written in this form. You need to understand that that number following is not the atomic number, it is the atomic mass. How does C12 differ from C13 and C14? The mass is going to be different, therefore the number of number of neutrons will be different. In this one, there will be 13 minus 7, or 6, there'll be 7 neutrons. 14 minus 6, this one has 8 neutrons in the nucleus. That's the major difference. And what happens there, this is the last thing I'll talk about, isotopes can be radioactive. If having extra neutrons cause it to be unstable, atoms don't want to be unstable, it's this term radioactive isotopes. So we'll talk about that. I'm going to stop there because I think I'm getting near 15 minutes. So what will happen is we'll pick this up tomorrow in class, or I'll make another video to kind of finish the rest of this portion that you need to know. All right? See you tomorrow.